So in this session, we are going to discuss about quantum gates. So in week 2, so this is a session outcomes. What is quantum gate? Quantum logic networks, gates without superposition, controlled knot, Toffoli gate, and square root of knot. Not 1 by 2 unitary implementation, Hadamard transform, and optical implementation of N1 by 2. So quantum logic networks invented by Dutch in 1989. So this is analogous to classical Boolean logical networks. Generalization of Frederikin Toffoli reversible logic circuits system is divided into individual bits or qubits. Two orthogonal states of each bit designated as the computational base states of 0 and 1. So quantum logic gates, local unitary transforms that operate on only a few state bits at a time. Computation via predetermined sequence of gate applications to selected bits. Gates without superposition. All the classical input consuming reversible gates can be represented as unitary transformations. Example is input consuming NOT gate inventor. Controlled knot is going to throw the input consuming XOR. So this is the truth table which is going to reveal the get 0 and get 1, which is going to hold the combinations of ones and zeros. This is a Toffoli gate controlled C naught. See here, there is a truth table which is holding some sort of explanation of three sort of inputs. So which is revealing some sort of information in terms of A, B and C, which is going to throw the complementary of again A, B and C. So this is the Toffoli's gates explanations. So whenever we are going to talk about this Toffoli, we have to keep in mind that so we are dealing with the three sort of inputs in terms of A, B, C. So where there is an unchanged information of A and B. So truth table is the bottom matrix shows the gates behavior for all the 8 input combinations. So question in the image is Toffoli gate is represented as the unitary matrix in quantum mechanics if the matrix elements are not restricted to 0 bar 1 binary, the gate can implement more general quantum operations, allowing complex amplitudes and superposition states beyond classical reversible logics. In short, the Toffoli gate flips the third bit C only when the first two bits A and B are both 1, and relaxing 0 and 1 restrictions let it become a broader quantum operations. So this is the Toffoli gate representation. So the next is this slide describes the square root of NOT gate in quantum computing, a single qubit operation that behaves like half of NOT operation. Action on basic states. When a qubit instead get 0 and get 1 passes through n1 by 2 gate, and the outcome becomes an equal superposition of get 0 and get 1, each with the probability of 50% upon the measurement. Applying two consecutive gates, feeding the output of this n1 by 2 gate into another n1 by 2 gate without measuring the inputs in returns of the qubits into original states. This is because n is the NOT gate that flips the get 0 to get 1. Why it seems so magic means the first n1 by 2 creates a superposition that looks random on measurement. However, the quantum state itself retains the phase informations. Applying the n1 by 2 reverses the operations, recovering the initial state because the gate is unitary and reversible. Next one is unitary implementation of the square root of naught, also denoted as square root of n in quantum computing. So this is the unitary implementation matrix. This matrix is unitary because so it is going to reveal the answer in terms of square root of n plus square root of n is equal to I, so which is going to closely related to the irrational numbers. So square relation is throwing some sort of thing for us. Thus applying this square root of n twice gives the ordinary dot operation. So action on basic states. The effect of this square root of n on the computational part of basic state is get 0 and get 1. Significance is the NOT gate is a fundamental example of quantum gate that performs of operation of classical bit flip useful in quantum algorithms and analysis of unitary implementations. So this is the unitary implementations. So next is Hadamard transformations. So whenever we are going to see the Hadamard transformation, we have to be very careful in stating the square root of identity gate used frequently in quantum logic networks. So another not 1 by 2. So this negates the phase of the state if the input state was get 0. So this gate is going to throw the additional phase effects. The matrix representation of this gate is given in its square root form. So applying this, we are going to get the twice matrix informations. So this is a NOT gate, which is an extra phase flip for the get 0 state. It negates the phase if the input was get 0. So the effect is the gate performs the half flip of the qubit. It is going to put it the superposition state of flipped and unflipped states. It is going to add the phase change of the specific to the get 0 input. In short, the NOT 1 by 2 gate is a quantum logic operations that partially flips the qubit and modifies the phase of the get 0 states. Next one is optimal implementation of the N1 by 2 beam splitter, semi-silvered mirrors from superposition of the reflected transmitted photon states. So a setup is a laser emits a photon that represents the qubit encoded in path of states 0 and 1. So beam splitter is going to throw some sort of action in terms of beam splitter, which is semi-silvered mirror creates a superposition of the transmitted 0 and reflected 1 photon paths. So inference is the two paths are recombined at a second beam splitter, causing the interference that flips the input state, input 0 and input 1, input 1 and input 0. So the result is the arrangement act as a quantum NOT gate, swapping the logical states of the photon. So this is the input states. So this is the universal Q gates. Dutch is going to reveal 3 bits. Next one is adequate informations. Next one is universal informations. So this is a Toffoli gate. So universal quantum gate that extends the standard Toffoli controlled NOT gate. So gate represented by 4 cross 4 unitary matrix where the parameters A and B are defined as A is equal to so and so, B is equal to so and so, where alpha is the irrational number, making the gate universal for quantum computation. Physical interpretation is the top 2 bits act as a control qubits when both control are get 1. The gate applies the unitary informations of AB, BA to the target qubit subspace for another control configurations. So the universality is the irrationality of alpha ensures that the gate can approximate any unitary operations to arbitrary precisions when combined with single qubit gates, making it universal gate in the quantum computing. So the next one is Berkone's 2-bit generation controlled gate where alpha, tau are relatively irrational. So this is going to work in terms of cosine and sine information. So this is a truth table which is going to replace the ket 0 and ket 1 with alpha, ket and gamma. So this is a Bernoulli results. So universality is going to reflect some sort of bit in terms of Bernoulli gate, which is already a universal, which is going to represent the 2-bit and 4-bit. So construction of generalized Toffoli gates are 3-bit version via 5-bit 2-bit gates. So n-bit version via orthogonal complexity, which is going to reflect the 2-bit gates. No auxiliary bits are going to be needed for this. All operations are done in place on input bits, and n-bit version via logarithmic of n, which is going to reveal 2-bit gates given 1 work bit. So these are all about all the gates which we have seen. So the universality is we are going to face some sort of summary in terms of irrationality of alpha, ensuring that the gate can approximate any unitary operations to arbitrary precision when combined with single qubit gates, making it a universal gate in quantum computing. So this is a derivations of how this gate is used in quantum circuits. Thank you all.